Hi, this is Physics 221, Mathematical Physics 1, and this is the first lesson of our course. And in this video, we're going to talk about your vector algebra. Let's review some basic ideas of vector algebra. I believe that you already know about this one in your previous math or in your previous physics courses. Now, again, you have here the notation of your vector. We shall denote or we shall indicate a vector with a boldface, like say for example this one, or with a letter. It's either capital or small letter with an arrow on the top. So as you can see here, you have your letter and then an arrow. So we either use your boldface letter or your letter with an arrow on top of it. Vectors can also be written like this one here. You have your parentheses. You have your components of your vector. Like say for example, for a two-dimensional vector, you have your ax and then comma ay. So you may either use any of this one to signify your vector. Now, the magnitude of the vector, or which is also called the norm of the vector, written as your a, just your letter a, okay, or written as your absolute value of your a is equal to your square root of your ax squared plus ay squared plus az squared. These are the sum of the square of the components, and then you get the square root of this sum. This is from your Pythagorean theorem, so you can get this one here. And for the addition of vectors, you can easily add vectors by adding your a plus b, okay, or you may have your a plus b plus c. And your vectors, they commute, so they follow the commutative law for addition. That is, your a plus b is equal to your b plus a. And if you have three vectors, your vectors also follow the associative law for addition. So like say for example, for vectors a, b, and c, so you have the quantity a plus b plus c is equal to a plus the quantity b plus c. So they are equal whatever way you add these vectors here. So you have here in this figure your vector a. This is how you draw your vector. So again, in drawing your vector, you draw it in, like say for example, in the Cartesian coordinate. So you have an arrow or a line with an arrowhead on the end. Okay, so at this point here, this is where you start your vector, and then the arrowhead will tell you the vector ends at this point. So the magnitude of your vector is shown by how long or short your line is. Okay, so in the xy plane, you can resolve this vector. So you have your x component here, and then here you have your y component. Okay, this is how you're going to add vectors. If you can remember, you add vectors, can add vectors graphically, or you can also add vectors using your component method. So again, you can add vectors using, let me just write it here. You can have, let's say for example, your head-to-tail method, or you have your parallelogram method. So you have geometric addition or graphical addition. You have graphical or geometric. And then you have your component method. Okay, so in here, if you have, say for example, two vectors a plus b, so you can just add it by graphical method by using your head-to-tail method. You have your a, and then from the head of a follows the tail of b, and then you have your a plus b. Now the sum of these vectors, two vectors, is just from the tail of a up to the head of b. So that is your a plus b. Or you can add the components. You have your ax plus your bx, and then your ay plus your by. Okay, so this is here the sum of this one, and the sum of this one are the components of your or the components of the sum of your two vectors a plus b. And here, this just shows you how your vectors commute, or how your vectors follow the associative law. So you have here your a plus b. This is the same with your b plus a. If you have your a plus b plus c, okay, so you have your a plus b plus c. So this is your a plus b plus c. You can add it by having your b plus c first, or you can also have your a plus b, which is equal to this one here, and then lastly you add your a plus b with your c. So this just shows you your associative law and then your commutative law for addition. You can also multiply vectors simply by multiplying a vector by a constant, and then, like, say for example, your constant is 3. Okay, this is your vector a here, and you multiply this vector with a constant c, just a number 3. So what you do is you multiply the magnitude of the vector times 3. So this vector here will be 3 times longer after you multiply it with a constant c. So you can multiply a vector by any constant c here. So you have your ca, okay, and it can be drawn something like this one here. And again here, c is any real number. Your unit vector, you can write it, or your unit vector is, this is a vector with length or magnitude 1. Unit vector is a vector with length or magnitude 1. Okay, so if you're familiar, you can, if you have your, say for example, this one here, for your vector a, so your unit vector can be written as something like, you have your a hat, and then you have your vector a divided by the magnitude of a, or just a. This is the same with your r hat, which is equal to your vector r over the magnitude of your r. Okay, so those are your unit vectors. Subtracting vectors, it's just like your simple subtraction. But in here, let's say for example, we have this one here. You have your a and then plus b. So here your b is downward, so your a plus b is equal to this one here. But if you say that you have your a minus b, this vector here, you're going to change the direction of this one, multiply it with a negative 1. So if you're going to change the direction of this one, it will now point upwards. So your a minus b is this one here. Okay, so that's your subtraction of your vectors. Now, I've said earlier that you can add vectors graphically, geometrically, or using your vector components. So let's first discuss how you're going to write your vectors in terms of its components. So if this is your vector a here, in the Cartesian coordinate, it has x component, and then it has your y component. Now this one here, these are your unit vectors in your Cartesian coordinate. They were written as bold letters, but you can write it like this. So along the x, you have your I hat, your unit vector I hat. Along the y, you have your unit vector j hat. And then along the z, you have your unit vector k hat. So in some books, you can see the hat symbol. But in some books, you can only see your bold-faced letters. But again, they're just the same. It's just that if you're going to write it, it will be hard for us to make a boldface in handwriting. So we label your unit vectors with your hat. Okay. So your vectors in terms of your components, you have, let's say for example for vector a, so you have I hat ax plus j, AY plus K AZ. Or yeah, let's write this one so you'll be familiar. Your vector A, this is how we write it using our hands. You have your vector A is equal to your AX, the component, and then I hat, the unit vector along your X component, and then plus your AY J hat plus your AZ K hat. If you have another vector B, so your vector B is just your BXI hat plus BY J hat plus BZ K hat. So if we're going to add these two vectors, let's say you have your A plus B. So this is just equal to adding the components of your vectors. So you add this one, your X components, and then you add your Y components, and then you add your Z components, just like your ordinary addition using your algebra. And you always carry the unit vectors. So you have this one here. You have your AX, BX, and then your I or your I hat. You have your AY, BY, and then your J or your J hat, and then you have your AZ plus BZ times K or your K hat. So that is how you're going to add your vectors in terms of its components. Let's go to multiplication of vectors. So you can multiply vectors in two ways. Again, you have your scalar product or your dot product, and then you have your vector product or your cross product. So again, we have two ways of multiplying vector. We have two ways. First is you have your scalar product, which is also called your dot product, because the way you write it, the dot product is like this. You have your A dot B. So you have this dot sign there. That is why it's also called the dot product. And the second way is you have your vector product, which is also called your cross product. So it's called a cross product because you write it like this. You have your A cross and then B. So these two ways of multiplying your vectors are different because first one, the resulting the result is a scalar quantity, and then the second one, the result is a vector quantity. Let's first discuss your scalar product. Now, by definition, your scalar product is just your A dot B is equal to the magnitude of A times the magnitude of B and then cosine theta. Now, your A dot B, that is equal to your B dot A. As you can see here, if these are your two vectors, if you have here your vector A and then you have here your vector B, what the scalar product or the dot product do is that if, let's say, for example, you have your A dot B, so you have your vector A times the projection of A onto B. So you have your vector B here. We project your vector B onto the axis of A, and then this projection, which is this one here, if you're going to project this one, let me line up this one. So the projection is actually equal to this one here. Now this projection with respect to the angle theta, that is equal to B cosine theta, right? That is the x component of your B. Now the dot product is your vector A here, the magnitude of your vector A, times your B cosine theta. So that is your dot product. We can also do your B cross A. Your B cross A is just your B times the projection of A onto B. So this time we take your vector A, we take this one here, and then we project this one onto the axis of B. And then as you can see, this one here is the projection of A onto B. So this is, with respect to this angle here, theta, this is A cosine theta. And then we multiply that one with, we multiply it with your vector B. So your A cosine theta and then vector B. For example, here you have, this is one for your vector A. This is 1, 2, 3, 4, 5, 6. So you have 6 as the magnitude. So the magnitude of your A is 6. And then for your B, you have 1, 2, 3, 4, 5, 6, 7, 8. So the magnitude of your B is 8. Okay, so what's the projection of, or let's do first your A, that B. Let me erase this one first. So we have space. What's A dot B? So what we do with A dot B is you have your magnitude of your A, and then you multiply it with the projection of B onto A. So the projection is this one, which is equal to 1, 2, 2, 3, and then 4. So 4 units, the projection. So this is equal to 24. Let's do your B dot A. So you have the magnitude of 6, which is 8. And then we project your A onto B, which is this projection here. And you have 1, 2, 3 units. So times 3, so you have your A times 3, that is equal to 24. Or you can just simply have your A be cosine theta, which is your 6, and then A cosine 60 degrees. And we should also get 24 there as the dot product or the scalar product. So 24 is just a number, just a scalar quantity. Your A dot A here, that is just the square of your the magnitude of your A. And if you have your A dot your B plus C, you just multiply A with B, or dot product A dot your A to B, and then plus the dot of A and then C. So that is A dot B plus A dot C. In its components, remember again the components of your vector A and then your vector B. So again, you have, if let's say again you have your A is AX I hat plus AY J hat plus AZ K hat, and then your B as your BX I hat plus your BYJ hat plus your BZ K hat. Okay, the dot product is just the product of the components, and then you sum your components. So as you can see here, this is the dot product is just equal to your AX BX plus AY BY plus AZ BZ. Okay, and I will leave this to you as an assignment to prove. But your unit vectors, when you're going to dot your unit vectors, if say for example you have your I dot your I, what's the magnitude of it again of your unit vector? The magnitude of your unit vector is just 1, so you have your 1 times 1 and then cosine. The angle between these two is 0 because they point in the same axis. And 1 times 1 times cosine 0 is just 1. So all the unit vectors here of the same direction is equal to 1. And if let's say you have your I, that your J hat, you have 1 times 1, and then your cosine, the angle between the two is 90 degrees because they are perpendicular. And cosine 90 is 0, so you have here 0. If you have the same unit vectors, and then you dot those directions, your unit vectors, you have your 1. If they're perpendicular, you have 0. So the angle between the two vectors can be found using your definition of your dot product. So again, you just have your A dot B is equal to AB cosine theta. So you want to find this angle here, so you have cosine theta is equal to your A dot B over the product of the magnitudes of A and then B. For example, find the angles between the two vectors. Your first vector is 3, 6, 9, and then your second vector is -2, 3, and then 1. Your A dot B is just the product of the components. So you have here your, for reference, you have your AX BX plus your AY BY plus your AZ BZ. Okay, so you have 3 times -2 plus 6 times 3 plus 9 times -1. So that is equal to 21. But from the Pythagorean theorem, the magnitude of A is equal to d squared of 3 squared plus 6 squared plus 9 squared, which is, let's take the 3 times square root of 14 answer. And let's not round it off if we have this one here. And for B, you have the magnitude of square root of 14. To get your theta, you have cosine theta of A dot B over A times B. So you have 21 over 3 times square root of 14 times square root of 14, which is equal to 1/2. So we have, you have here cosine theta, which is equal to 1/2. To get your theta, we just take the cosine inverse of 1/2. So that is now equal to your theta, which is equal to 60 degrees. Two vectors A and B are perpendicular. That is, A is perpendicular to B if the dot product of the two vectors is 0. That is, you have cosine 90, so cosine 90 is 0, so the dot product A dot B is 0. And two vectors are parallel, that is, A is parallel to B if the components are proportional and you have some proportionality constancy between the two vectors. You can verify if the two vectors are parallel if the ratio of AX and BX is equal to the ratio of AY and BY, and this should also be equal to the ratio of AZ and BZ. And this ratio should be somewhat equal to C, and you have that proportion between the two vectors. So that is how you're going to verify if the two vectors are parallel. The second way of multiplying your vectors is your vector product. By definition, your vector product is just your A cross B, okay? And your A cross B is equal to AB sine theta, okay? Where your A cross B, which you can say is equal to C, is perpendicular to A, the plane of A and B. So as you can see here, that if this is your vector A and then this is your vector B, the result of your vector product is a vector which is perpendicular to the plane of A and B. If this is here the plane of A and B, so your vector C, which is the cross product of A cross B, is perpendicular to both A and B, or to the plane of A and B. A cross B is 0 if A and B are parallel, because from here, if they're parallel, sine 0 or sine 180, that is equal to 0. So your A cross B is 0. So that also means that your A cross A is 0 because they are just the same vectors and they point in the same direction. Thus they are parallel. And by the way, your A cross B is not equal to B cross A, but instead you have your A cross B is equal to the negative of B cross A. You can get the direction of your vector product using your right hand rule. So I'll give it to you as an assignment to review how to use your right hand rule. Now your unit vectors, when they cross, you have, if they are in the same direction, again you have your I cross I, that's equal to J cross J, and then you have your K cross K, that is equal to 0. Again, that is because you have here sine 0, which is equal to 0 for this case. If you have different vectors and unit vectors and then you cross them, your I cross J is equal to K, and then your j cross k is equal to I hat, and then your k hat cross I hat is equal to j hat, and your j cross I is equal to negative k hat. You can use this one here. You have your ijk, or you can also use this one, your ijk. If you are going to rotate counterclockwise, your answer is a positive. If you're going to rotate clockwise, your answer is a negative. So let's say, for example, here, your I cross j will rotate counterclockwise. The answer is k hat. And if you have j cross k, the answer is I hat. And then if you have your k cross I, you have j hat, which is the answer. If we do a clockwise turn, if you have your I cross k, the answer is negative j hat. If you have k cross j, the answer is negative I hat. If you have j cross I, you have negative k hat. The cross product of your vectors, for the same vectors a and b, is equal to this one here. So you have your a components cross with your b components. You just distribute this one, distribute these terms here to the other side. Okay, and then you do cross product of the unit vectors, and then you just simply multiply the magnitudes. Or you can also use the determinant method to find for the answer of a cross b. So you write your vector components in a matrix, and then you find for the determinant of your matrix. So what's the determinant of your matrix, or what's a cross b in this case? What we usually do is we extend this one. So you have your I hat and then your j hat. Of course, you have your hats here, and then you have your ax, bx, and then your ay, and then by. So your a cross b, that is just equal to this one here first. Okay, so you have, I usually cover that one. So I have, I'll multiply this one minus this one. So I have your ay bz minus your az by, and then times your I hat. And the next thing that I like to do is I cover this one, and you have the product of this one minus this one. So next we have plus your az bx minus your ax pz, and you have your j hat because that is what I covered. And then plus, next thing I like to do is I just cover this one because it's easier. And then the product minus the product of that one. So I have ax by minus ay bx, and then times your k hat. So that is your cross product. For example, find a vector perpendicular to both A and B. For S of a vector perpendicular, so that is your S of A cross B, right? So what you just do is, you can use the matrix, or you can use another way, which is to distribute your terms. Or if you are going to use your matrix, you write your vectors in a 3x3 matrix. So you have your I, j, k first, your unit vectors, or your I hat, j hat, k hat, and then next here you have your ax 2, your ay 1, and then your az negative 1, and then you have here your b components on the third row. And then you do your cross product, you get this answer here. You can pause this video to verify if indeed that is the right answer. Okay, so I'll just leave it to you. So again, these are your vector products, or sorry, your vector multiplication. So you have your dot product and then you have your cross product. So some applications of this one, you're familiar with your dot product that is usually applied in your work. So your work is, you have your two vectors, your force and then your displacement. So your work is the dot product of your force and then your displacement. For infinitesimal changes in your work, you have your F dot, your dr. Your cross product is applied on your torque. Okay, so you have your R cross F, your lever arm, and then your force. And it's also applied in angular velocity. You have your V is equal to your omega cross R. These are some of the topics in mechanics which use your dot product and then your cross product. We have also this what we call your triple products. And the first of these triple products is your triple scalar product. It's a triple scalar product because the answer is a scalar quantity. You have your here your scalar product, triple scalar product as your A dot your B cross and C. So you can write this one to solve it in a matrix. On top are your A components and then your B components and then you have your C components. To solve this one, you just need to find the determinant, the same method that we used earlier in solving for your cross product. It's just here that your AX, AY, and AZ were before your I hat, your J hat, and then your K hat. Okay, and you can visualize this one. You visualize this one by constructing a parallelepiped. Okay, so if these are your three vectors, you have your vector A, B, and C. So again, the cross product of these two vectors A and B, or sorry, the cross product of your B and C, which is equal to your B sine theta, BC sine theta, is the area of this parallelepiped here, of the surface of the parallelepiped. So your B cross C is this one here. That is the area of that region there, or the area of the parallelepiped with sides B and C and angle theta. Okay, and this one, if you were able to evaluate already, you're able to evaluate this one already, and then you dot product it. Now you see here that this is actually you can write this one as your A cosine theta, and then you have your B cross your A. And here, your A cosine theta is just the height of your parallelepiped. So that height there is this one here, the projection of A onto B cross C. There again, the area of your B cross C is this area here, but your B cross C is perpendicular to that area, which is this one here. This is your B cross C. And your vector A, if you dot product it with this vector B cross C, you project your vector A onto B cross C. This is this projection here. And this projection is the height of your parallelepiped. And as you can see, if you have your area times the height, that is equal to the volume of your parallelepiped. Okay. So let's evaluate your triple scalar product. So we just again wrote it in a matrix, a 3x3 matrix, and then we find for the determinants. There's other way to find your determinants, but I use this one because it's much easier for me to remember things. So again, I extend this one. You have your AX, BX, and then your CX, and then we have AY, BY, and then your CY. Okay, so first things first, I cover this one, but I retain your AX, the topmost part, and then you get the product of this one minus the product of this one. So you have your BY CY minus your BZ. Sorry. This is, again, let's do it again. This is BY CZ minus your BZ CY. And then you have plus. So I again cover this one here, but I retain AY. And then multiply BZ and CX, and then minus this one. So I have BZ CX minus BX CY or CZ. And then lastly, you have plus, you know the drill. So I cover up this one, but I retain your topmost part, AZ, times your BXCY minus your BYCX. So that's the answer for your triple scalar product. Okay. For example, find the volume V of the parallelepiped with size A, I hat plus 2j plus 3k, and then B, 4i hat plus 5j hat plus 6k hat, and C, you have your 7i hat plus 8j hat plus 10k hat. Okay. Please solve this one on your own. You may pause the video for a while. And I'll just tell you the answer. I hope you get an answer of 3. So that's the answer for this problem. So I'll let you do it yourself. So you try your triple scalar product. Your triple scalar product can be seen in the formula in finding the volume of a unit cell for reciprocal vectors. So these are your reciprocal vectors. And as you can see here, you have here your triple scalar product. You learn more of this one, and these formulas will be more familiar to you when you have more, when you go into your solid state physics class or in a crystallography class. So these are the volume. Your triple scalar product again is used in the volume of the unit cell for your reciprocal vectors. Now the next one, the next triple product is your triple vector product. It's called the triple vector product because the answer of this one is a vector quantity. So your triple vector product is just your A cross B cross C. And then before we evaluate this one, let's have some observations. If this is your vector B and then this is your vector C, you see that your B cross C is perpendicular to the plane of B and C. That is, your B cross C here is perpendicular to both B and to C. So this one here is your B cross C. And if you're going to evaluate your A cross your B cross C, anywhere, wherever your vector A is, if say for example you have, let's say some vector A here, okay, anywhere your vector A is, you'll see that your A cross B cross C is perpendicular to the plane of A and B. And in the figure, any vector perpendicular to B cross C lies in the plane perpendicular to B cross C. So that is your A cross B cross C is some vector in the plane of B and C. So you can actually find your A cross B cross C somewhere along this this plane here. Okay, so if that is the case, if your A cross B cross C lies on the plane of B and C, then that means we can then that means that the answer of this one, your A cross B cross C, can be written as something like your A times B plus B times C. Because again, the answer of your A cross B cross C lies in the plane of B and C. So that means you can write, or the answer of A cross B cross C is something like your A times B plus B times C, where your A and B are scalars that you want to find. You can verify this one using your right-hand rule, and you'll see that indeed your A cross B cross C lies somewhere around this plane here of B and C. Let's evaluate your triple vector product. And one way to find A and B previously is using your component form. So we'll use your component form. Remember again that this one here, this is equal to AB plus BC. And we're going to find this A and B using your components. Okay. And you can simplify this work by choosing our coordinate system carefully. Let's say that given your three vectors A, B, and C, we take your vector B as where your x-axis is. So if where your vector B is the x-axis, then we write your vector B as your bxi hat. So it only has the x component. So we're doing this one to simplify the work, and you'll see later. And we take where your y-axis is in the plane of B and C. If this is the plane of B and C here, okay, if this is the plane of B and C here, we take your y-axis around here. You can say that your vector, we cannot say that your vector C is in the y-axis, because let's say that this is just an arbitrary vector in an arbitrary direction. So let's say that you have perpendicular to this one is your y-axis in your BC plane. And if that is the case, then your vector C can be written as this one. So it has components, your Cxi hat plus your Cyj hat. That is, we can project your vector C on the xy plane. And your vector A, since we do not know about that one, we don't have any information about that one, we write it as your Axi hat plus Ayj hat plus Azk hat. And take note that perpendicular to B cross C is your B cross C here, this vector here, this specific vector here. And let's call this one as your z-axis, where your z-axis is. Okay, so again, your x-axis is where your B is. That is your vector B, is just your bxi hat. Your y-axis is in the plane of BC. And then your x-axis is perpendicular to the plane of B cross C. Okay, so let's evaluate this one. So evaluating your A cross B cross C, let's evaluate first your B cross C. So we use these components here. Your B cross C, you have your this is equal to bxi hat cross let's write again. You have your b xi hat cross with cxi hat plus cyj hat. Okay, and your I cross I is just 0, so you are left with your I cross j, which is equal to k. So your B cross C is equal to bxcy k hat. And then use this one to get your A cross B cross C. So we have AXI hat plus AYJ hat plus AZ K hat, and then cross your, this quantity here is crossed with BXCY K hat. So I'm not going to solve it. I'll just give you the answer of your A cross B cross C, and it's up to you to verify if that is indeed the right answer. The answer to this one is you have your AX BX CY negative J hat plus AY BX CY and then I hat. Okay, so that is the answer, but we can rewrite it so that we'll have this form here. So on the previous slide, we have your AX BX CY. This is negative J hat plus AY BX CY, and then this is I hat. We can rewrite it so that we have a combination of B plus C. I want it to look like this. I have a combination of vectors B and C. So we can rewrite it like this. You have your negative AX BX, and then I want to write CX I hat plus CY J hat, and then plus your AY CY plus AX CX BX I hat. Okay, and as you can see, your AX BX is just your A dot B. Your CX I hat plus your CY J hat is just your vector C, and your AY CY plus your AX CX is just your A dot C, and your BX I hat is just your vector B. If those are your constants, so you can write your A cross B cross C as something like the negative of, you have your AX BX, so you have your A dot B cross C, or times C, sorry, times C, plus here, this one here, this is just A dot C, right? Sorry, this one here is C, this is A dot C, sorry. So you have your A dot C times your vector B. Okay, or you can write this one as your B A dot C minus, you have C A dot B. So you have your back minus cap. So it's back minus cap. Okay. So that's your triple vector product. So your A cross B cross C is equal to B times A dot C minus C times A dot B. So you have your back minus your cap. Your vector triple product is not associative. So that is your A cross B cross C is not equal to your A cross B cross C. You have here your A cross B cross C, your back cap. Okay. But your A cross B cross C is equal to this one here. You have back minus ABC. So it's not associative. And it can also be shown that for any three vectors A, B, and C, your A cross B cross C plus your B cross C plus A plus your C cross A cross B is equal to 0. Some application of your triple scalar product, you use it in your torque, but for the general case wherein you find the torque produced by a force about any given line L. The application of your triple vector product is in your angular momentum. You have your angular momentum L is equal to your R cross P, but you can write this one as your MR cross V, and your V is you have your omega cross R, so you have your R cross omega cross R. And it can also be used in your centripetal acceleration, which is equal to your omega cross R. And lastly, you have your reciprocal vectors. You have seen this one earlier. You have the formula to find for the volume of your unit cells. Two sets of vectors A, B, C and A prime, B prime, C prime are called reciprocal sets if your A dot your A prime is equal to your B dot B prime and is equal to your C dot C prime and is equal to 1. And they are reciprocal sets if your A prime dot B is equal to your A prime dot C, and then your B prime dot A is equal to your B prime dot C. It's equal to C prime dot A, and your C prime dot B, they are equal to 0. So the reciprocal vectors of A, B, and C are the following. So the reciprocal vector of A is A prime is equal to B cross C over A dot B cross C, and your B prime is equal to your C cross A over your A dot B cross C, and then your C prime is equal to A cross B over A dot B cross C. Say for example, you're asked to construct the reciprocal vectors of A, 2i hat, and B equals j hat plus k hat, and C that's equal to I hat plus k hat. So you just use these formulas here. You first find your triple scalar product, your A dot B cross C, and then you use these formulas for your A prime, B prime, and then your C prime, the reciprocal vectors of your A and B. I will not be solving this one. I will give it to you as your assignment. Please verify it so you can practice. Your A prime, okay, your A prime is equal to 1/2 I hat plus j hat minus k hat, and then your B prime is equal to j hat, and your your C prime is equal to negative j hat plus k hat. So please try solving it yourselves. So I'll be giving it to you as your assignment to verify this, the answer to this problem. So we're going to end here for our lesson in vector algebra. In the next lesson, we're going to discuss your vector calculus. Thank you for listening.